before starting the today's lecture, first we quickly go through the last day's lectures answers of the quiz. The first question was, why binary number system is used for most digital system. Now, as we know, the most of the digital systems use discrete number of parameter levels, say the voltage levels or current levels, and the finite number of values in a digital system can be represented by a vector of signals with just two values. This is the binary signals, means that 2 that can be represented by a string of 0 and 1, 0 0 1 0, or 10 that is 1 0 1 0. And the device which processes this signal is very simple to implement, say a switch, either 0 or 1 means switch on or off or open or closed. So, that is why that mainly binary number system is used for most of the digital systems. Second question was the conversion, the following binary numbers to decimal. So, as here the binary is in binary radix is 2. So, using the formula we did, this should be 10101 means 1 into 2 to the power 4, 4 is the place value. Similarly, 0 into 2 to the power 3 plus 1 into 2 square, 0 into 2 to the power 1, 1 into 2 to the power 0, and the non-integer part 0 into 2 to the power minus 1, 0 into 2 to the power minus 2, 1 into 2 to the power minus 3. So, if we do this computation, we are getting 21.125 in decimal number system. Similarly, the other one also, similarly we can get that it is 50.3125 in decimal number systems. Third question was the convert the decimal numbers to binary. So, the first one was 678 in decimal. So, in this case we will divide by 2, as I want the number to be converted in binary system where the radix is 2. So, divide by 2 and this will be a repeated division and we are accumulating the remainders. So, 678 divided by 2, remainder is 0. For the second division, remainder is 1. Similarly, I am getting these remainders. Again it is continuing here, 21 divided by 2, actually it will be remainder is 1, remainder is 1, then this next remainder is 0, next is 1, like that, and what we will be getting the answer. This is 678 in decimal number system. 10 is that we have to take the remainder in reverse way, that means 10101 00110. So, this is the my in binary. And the B part, answer of the B part is there is one non-integer portion also. So, the integer portion is similarly by repeated division we will get that the integer portion, that 129 in decimal number system is 100000001. We can take in, we can see this thing in other way. See that actually the place value here this is 0, 1, 2, 4, 8, 16, 32. So, these are the places, just a minute. See, if we take the here, this value will be 128 and this value will be 1. So, this is 128 plus 1 because rest of the digits are 0. So, this is 129 in decimal number system. Now, the non-integer portion I can get by repeated multiplication by the radix value. So, this is the first non-integer is 0.84, it will be multiplied by 2, then it will be 1.68 and integer is 1. Similarly, I will get again the non-integer portion multiplied by 2, another integer 1, and in that way I am getting that this is 0, this is 0. So, the non-integer portion 0.84 in decimal, it will be 0.1100 in binary. So, the number 129.84 in decimal is converted to binary, the binary number is 1000001.1100 and this is approximated. Now, the last question was the conversion from decimal and binary numbers to binary coded decimal, the BCD value. Now, see that the first number was a 5648 in decimal. So, the way we have defined the binary coded decimal will take that for each decimal digit the 4 such binary values. So, that means here 5 means say this is a 0101, 6 means this is a 0110, 4 means 0100, 8 is 1000. So, this is my BCD. Now, the part B is a binary number, already it is a binary number is given. This is 100001101 in binary. Now, what is the decimal equivalent of this? Because this is 1, this is 4, 8, 16, 0 into 16, 0 into 32, 0 into 64, this is 1 into 128. That means, the value is 141 in decimal. Now, once it is converted into decimal, now the same way that each digit is replaced by 4 binary digits. That means, 1 means 0001, 4 is 0100 and 1 is again 0001. So, this is my binary coded decimal value. So, these are the answers of the lecture 3 quiz. Now, we start our today's lecture, the digital logic 2. First, we see the accuracy of binary conversion of non-integers. See, when a non-integer decimal is converted to a binary number, sometimes we truncate the number of digits by n. Say n can be 4, that means after decimal points I can take 4 digits, I can take 5 digits or say 9 digits, but still it does not stop, that means that fraction part does not become 0, but we stop. this is called the truncated to some n digits. Then obviously there will be some errors, because if we increase the number of bits, then we will be nearer to the actual value, we will be nearer and nearer to the actual value. So, now this is called, we are defining as if this is a error. That means, if I take up to after decimal points, if I take after 5 digits, I will be getting a more accurate result. Instead, if I take 3 digit value. Now, the maximum error in this decimal is defined as 2 to the power minus n if it is truncated by n bits. See why we are telling this thing. See, a binary number is expressed as say 0.1010 I, j, k, l, like that. That means, say here after decimal point I am taking 1, 2, 3, 4, 5, 6, 7, say 7 bits, 7 such bits. I, j, k can be 0 or 1. Now, see, as this is a it is converted to a binary number systems, that is why I, j, k are 0 or 1. Now, up to 4 bits already the 1 or 0 value is there, but from the 5th bit onwards I have represented the bits as I, j, k like that. That means, I, j, k can be either 0 or 1. Now, if the 5th bit and all succeeding bits are 0, then the number is accurate up to 4th bit position, because these are remaining bits are all zeros. So, what I can tell that this is 0 0.1010, then all are zeros. So, no need to write this thing. So, I can tell that this is 0 point, even it is up to 4th, or here in this case it is up to 4th bit position, this is correct. Now, see, if 5th bit and all succeeding bits are 1, then the error would be that 0.0000, and then these are all ones. So, actually these are not zeros. If it is 0, we can easily discard those values, but if I, j, k these values are 1, then I cannot discard that, then actually I am approximating that values. So, there must be some error introduced in the binary number. And what is that error? And that error is that up to 4th decimal point it was, the value was given in binary. So, now I am taking as if these are all 0, and these I, j, k values and succeeding values are 1. So, actually these are the where these values were actually present, or it should be incorporated in the binary number, but we have dropped this value from the binary number. So, that is why it is this is defined as an error. Now, we see that how we have approximated this thing. See, in decimal the error is E10. How it is coming is 2 to the power minus 5, 2 to the power minus 6, 2 to the power minus 7 plus 2 to the power minus 8. We see the previous slide again. See, actually I have dropped the 5th bits and the all succeeding bits, and if they were all ones, then it was, we have defined this as the error. Now, see, this is the place value, this is after decimal point, this is the 5th bit. So, it will be 1 into 2 to the power minus 5. The second one is 1 into 2 to the power minus 6, and that I was getting here. See that this is 2 to the power minus value, the 5th bit. This is the error for the 6th bit, 1 into 2 to the power minus 6, 2 to the power minus 7, 2 to the power minus 8, and so on. Now, if I take common the 2 to the power minus 5, then it will be 1 plus 2 to the power minus 1, 2 to the power minus 2 plus 2 to the power minus 3, like that. Now, that this term within the parenthesis, this term is a geometric series, and it approaches a value nearly equal to 1 divided by 1 minus 1 by 2, and which is nothing but the 2. So, this value, this within the parenthesis, this value becomes, becomes 2, and so what will be the value of E10? This is 2 to the power minus 5 and multiplied by 2. So, this value is 2 to the power minus 4. So, if n bits, in our example we have tried n equal to 4, that means up to 4 bits the binary number was given, or it was truncated, the number was truncated up to 4 bits, after decimal point the 4 bits were taken. So, if n bits are used to represent the non-integer part of a binary number, then the maximum error due to termination is E10 equal to 2 to the power minus n. That means, here 4 is replaced by n in general cases. So, this is the, this we are telling that accuracy of a number when it is converted from decimal to binary. Now, last day we have read that what do we mean by octal numbers, what do we mean by hexadecimal numbers or octal number systems, hexadecimal number systems, etc. Now, today we see another type of binary number systems, what we call that binary coded numbers. Why? Because already we have mentioned that mainly the computer handles, or it is very advantageous if the it is all the numbers that are used in computer is represented in a binary number systems. So, even it is used in octal or hexadecimal, how they are converted into strings of zeros and ones, means mainly the binary values, only 2 values, then obviously it will be very much, it is very easy to implement in for digital systems. Just the simple example I have given, that one switch always we can model as a switch on is 1, switch off is 0. That means, this is the binary system. So, first we see that what is binary coded octal, normally we call BCO. So, for octal number system already we have seen that the base or radix is 8, and the 8 symbols are that 0 through 7, means 0, 1, 2, 3, 4, 5, 6, 7. These 8 values are mainly used. Now, the computer uses binary coded octal, already I mentioned. Now, how this octal number is converted to binary coded octal? That is, see, 3 binary positions are used to represent 1 digit of octal number. Let us take an example. Say the example I have taken, this is octal is 23237, that is in octal value. Now, each positions, say these positions, that second position value is 2 in octal, that will be represented by 3-bit binary, means say 2 means our binary, if I take that 2 binary of 2, how I can do that thing? That again if I it should be divided by 1, then it will be 1 0. So, if I take this value, this will be 1 0. So, if I want to represent 2, if I want to represent 2 by 3 bit binary numbers, this will be 0 1 0, the leading bit I have given 0, it is of no meaning. So, 0 1 0. So, the BCO of 2 is 0 1 0. Similarly, the 3 we can represent as 0 1 1 and the 7 is 111. So, the octal 2378 that gives the binary coded octal, that 0 1 0 0 1 1 1 1 1. Now, it is very much advantageous if I want to convert that thing to simple binary, and what we will be doing, that we will suppress the leading zeros. See here only one leading zeros are there, say only this is a 0. So, the binary will be value will be only 1 0 0 1 1 1 1 1. So, the advantage is that it is very easy to convert from binary to BCO or BCO to binary, and that is why these are very much used in the computer systems. Now, again some other different examples we take, that this is 159 in decimal number system, this is 159. So, first this is converted into the binary, that 1 0 1 1 1 1 1. Now, what I can do, that as it is a binary, actually I am doing the reverse thing, now binary to BCO. So, what I will be doing, we know that the 3 digits I have to take together. So, this is from, if I start from the LSB side, from the right hand side to left, then this 3 is grouped, this 3 is grouped, and see only 1 1 is left. So, what I can do, I can put say 2 zeros here, because inserting 2 0 in the leading position does not affect, because it means that value is 0. So, how I group in 3 bits, this is 0 0 1, this is 0 1 1, this is 1 1 1. So, now if I convert 0 0 1 means we know that this is 1, this is not 2, this is actually 0 0 1 means this is 1, then 0 1 1 means this is 3 and 1 1 1 means this is 7. So, this is my 137 in octal value. Now, if I take another example 67258 in decimal number system, then first it is converted to say that decimal binary numbers. So, this is 1 1 0 1 1 1 0 1 0 1 0 1. So, Okay, one thing is better I take this as the octal. Okay. So, we are taking this as the octal value. So, this is 6725 and the base is 8. Now, what we will be doing? Again that each digit in octal, that should be represented by 3 binary bits. So, this 6, this is nothing but 6 represented in 3 binary bits. This is 7, this is actually 2 and this is 5. So, this is my BCO, binary coded octal. What will be the binary? Because there is no leading 0, no leading zeros are there. So, if I just merge these 3-bit numbers, then it will be my binary, that 1 1 0 1 1 0 1 0 1 0 1. This is my binary numbers. Now, we consider one fraction. So, this is 2.51 in octal. Then what I will be doing? As this is there are 2 portions. This is my integer portion, this is my integer and this is my non-integer portion, non-integer portion. So, in integer portion we will be doing the 2 is represented by 3 binary bits 0 1 0. Now, the non-integer portion will be again similarly can represent it. So, 5 means 1 0 1 and 1 means 0 0 1. So, this is my binary coded octal, and what will be the binary? Again the one leading 0 is there. So, we just drop the leading 0 and we merge. So, this is 10.101001 in binary. So, we see that how that one octal value can be converted to one binary coded octal value, and from there that binary coded octal value to binary. So, what we can tell that octal to binary or BCO, binary coded octal to binary, and the advantage is that the ease of conversion. So, that is why that BCO is very popular. Now, the similar number system is the binary coded hexadecimal, because similar to octal already we have read another number system, that is hexadecimal number system, and there that hexadecimal means the base is here, the hexadecimal, the base is 16, and we have seen actually 0 to 15 values from 10 to 15 are actually represented by 10 means A, 11 is B, and similarly that 15 means F. So, 0 to 9 and A to F, these 16 digits are the symbols of hexadecimal system. Already we have read in the last class. Now, we see that how this binary coded hexadecimal, that means how these hexadecimal numbers are converted to into binary coded numbers. This is very similar to our BCO, the binary coded octal. Again we take one example. So, this is my hexadecimal numbers A to 9. So, A means 10. So, if I want to convert that thing in decimal, the 10 into 16 into square, because A's position is 2, 2 into 16 to the power 1 plus 9 into 16 to the power 0, which becomes 2601, 2601 in decimal number system. Now, the same number if I want to convert in BCH, now in this case each hexadecimal digit will be represented by 4 bits. These are every one will be represented by 4 bits. In octal it was represented by 3 bits. So, this A means 10. So, this is 1010, that 10. 2. So, this is my 2 and this is my 9. So, this is the BCH code or binary coded hexadecimal code. And similarly, if I want to convert this thing by binary, then I will just drop the leading zeros and merge all the values. Here there is no leading 0. So, it will be 1 0 1 0 0 0 1 0 1 0 0 1. This will be the value. So, any base which is an integer power of 2, say 8 means 2 to the power 3, that means octal when base is 8, that is a power of integer 2, or 16 when base is 16 for hexadecimal case, this is power of an integer 2, fourth power of 2. So, then it can be converted in this way. This is a very simple way, but only restriction is that if the radix or the base is a power of integer 2. So, if we see another example, that 1E2 in hexadecimal number, then that this is 1 is represented by 4 binary bits. E means that 14 is represented by 4 bits and 2 is represented by 4 bits. This is called BCH. And what will be the binary? See, here there are 3 leading zeros. So, drop this 3 zeros, then it will start from 1 1 1 1, the 4 1, then 0 0 0 1 0 0 0 0 1 0. So, this is my binary number. So, that means from hexadecimal number you have converted to BCH, and from BCH to binary, again this is very simple, just drop the number leading zeros and merge the other binary values. So, this will give you the binary number. Now, we see that some other codes. One is called the alphanumeric codes. Now, alphanumeric codes or other characters are necessary in several instances. So far we have seen only the numbers, either it can be decimal number, either it can be octal number, or it can be hexadecimal numbers, but sometimes we need characters and some other control characters. Then how they can be converted into binary values 0 or 1 if it is used in computer. Say in our keyboard, all of you know that keyboard, that A to Z the 26 characters are there, 0 to 9 the 10 decimal values are there, and there are some more control characters, say some mathematical operators are there, less than, greater than, some question mark is there. Then how these characters or these alphanumeric characters, how they can be converted into 0 and 1. Now, there are many choices of code sets to represent alphanumeric characters and several control characters. Now, one well accepted code set is the ASCII, and the full term form is the American Standard Code for Information Interchange. So, this is a very well known standard in microprocessor work. So, we see that how this, what is this ASCII code? Okay. See, ASCII is a 7-bit code normally used in exchanging information. See, in our keyboard that when we press A, so actually A means immediately it is converted to a 7-bit binary numbers. This is predefined. This is a predefined numbers. Say this 1000001. This is my capital A. If I represent this thing in hex, it will be simple because just now we have done binary to hexadecimal means we have to group, it will be grouped by 4. So, here it is 4 and here another 0 I will put. So, 0100 means this is 4 and 0001 means this is 1. So, this is a hex 41. Similarly, the small letter a, that will be by this 7-bit value binary values, that 110 and 0001, and this is the hex is 61. Similarly, that all A to Z, I have given another 2-3 examples, that capital K, capital J, how they are defined. So, that means here as these are 7-bit ASCII, so 2 to the power 7 means that 128 such characters and control characters together, total 128 numbers I can represent by these 7-bit binary values. And always that just this is easy to express the hexadecimal because it is very smaller in size. So, the hexadecimal values are also given. See, this is the parenthesis, that opening parenthesis is given by these 7-bit binary values and the hex is 28. The closing parenthesis similarly it is defined these 7-bit numbers and these hex value is 29. Now, if it is a operator say less than or it is a greater than, then also that it has some ASCII code. So, we are telling this is the ASCII code of this 7-bit binary or the hex, these are the ASCII code of less than or greater than, say at the rate. So, this is the 7-bit code and hex code is 40. Similarly, the question mark, the ASCII code of question mark is 3F or this is the numbers. And so, for that in the keyboard whatever characters and the control characters, the mathematical operators, say some other special functions say F1, F2, F6, some del, acknowledge or home, end, everyone that has some ASCII code. So, when we are pressing this thing, immediately it is converted into that 0-1 values or strings of 0 1s, these are predefined and obviously it will be then realized as that particular A. Now, we see another 3 basic operation in binary system, because so far from our discussion what we have seen that mainly in computer or in digital systems we will be using the binary number system. Now, in binary we have only 2 values because binary the base is 2. So, it is the 0 and 1 value. So, there are only 2 values, that 0 and 1. So, first thing I have to define, if I want to define a binary addition. So, first how these binary digits are added. So, as there are 2 values, there can be, see, say in binary addition, say we have 2 values 0 and 1, 0 and 1. So, what are the different addition of digits? One is 0 plus 0 and we are defining this as a 0. Sum is 0, I am telling sum is 0 and from our normal sense that carry is also 0. That means, if we add 0 and 0, the sum is 0, carry is also 0. Now, if I add 0 and 1, then sum is 1, carry is again 0. And this is same because it is addition. So, 0 plus 1 and 1 plus 0 is same and the sum is again 0, 1, carry is 0. Now, if it is 1 and 1, because there are only 2 digits in the binary system. So, these are the 4 such different addition is possible. So, this is 1 plus 1, then sum is 0, carry is 1. So, if I know these basic additions of binary digits, then I can do any binary addition whatever large it is, but it is very simple. We see that thing. See, I have taken one example that these are my 2 operands, that 111, 101 and I am adding that thing with 101, 101. So, if it is 1 I am adding, that means my sum should be 0, carry should be 1. Then 0 plus 0, that is 0, sum is 0 and again that is added with another 1. So, that sum is 1, but carry is 0. Now, again here see that this is 1 plus 1 means my sum is 0 and that, but carry is 1 and again that sum 0 plus 0. So, this is 0, carry is 1. Now, we see this value that, so actually this is 1 plus 1, that sum is here for this I am getting 1 plus 1 plus 1. So, here 1 plus 1 means sum is 0 and carry 1, carry 1 and again this it will be added with this. So, 0 plus 1, this will be 1, sum is 1 and carry 1. So, sum is 1, carry 1. Now, again this is 0 plus 1, 1 and 1 plus 1, sum 0, carry 1. Now, if it is 3 1, that is similar, this is similar, 3 1 to be added, this will be sum 1, carry 1 and that should be come here. So, 1 plus 1 0, carry 1, again this is 1, 0 plus 0 plus 1 1, 1 plus 1 0, carry 1, 1 plus 1 plus 1 1, carry 1, 1 plus 1 0, carry 1, 1 plus 1 plus 1, carry 1, sum 1. So, this is my binary addition and these are the carries. These are my carries and these two are 2 operands. Now, if I know binary addition, then obviously the same rule I can apply to binary subtraction. We see the binary subtraction. Now, see that again if I write the addition rule, there the rules are 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, 1 plus 1 equal to 0, carry 1. So, here carry if you write 0 0 0 carry 1, this is my sum, the same rule. Now, see here I am subtracting 1 0 1 1 1 from the value 1 0 0 1 1 0 1. So, first if it is, see that 1 minus 1, that means see here I can take from here as if this one is say this one is subtracted from this, that means 1 plus 0 equal to 1. So, this if I subtract this thing, so 1 minus 1 equal to 0. So, the same thing I have done, 1 minus 1 equal to 0. Now, 0 minus 1, what do we mean by 0 minus 1? So, that means I have to take this one. So, 0 minus 1, that will be 1. So, the same thing I have done, 0 minus 1, it is 1. So, from our normal subtraction rule or the decimal system, that what we know, actually I borrow 1 because 0 is lesser than 1. So, I borrow a 1 and that is 1 0. So, these are my, this is my borrow for this subtraction bit. So, this is 1 is borrowed. So, 1 0, this is 1. Now, so this becomes 0 because I have borrowed. So, this is less, this becomes 0. So, now again 1 I have to subtract from 0. So, again it should be borrowed and this is 1 0. So, again it is 1 and it is again borrowed. So, this becomes 0. Now, see that 0 and 0. So, this 0 minus 0 is 0. So, actually here it is not, it is not borrow. 0 minus 0, it is 0, there is no borrow. Now, again 0 minus 1, 0 minus 1. So, again this is borrowed. See, one is 1 I want to subtract from 0. So, this should be that 1 subtracted from 0. So, this should be 1. Okay. This should be, again this is actually 1 0. So, this is 1. Again it is borrowed. So, this becomes 1 0. Similarly, this is 1 and again this becomes this 1. So, this becomes 0. So, 0 minus 0 0. So, this is my result. So, this is the binary subtraction. So, actually there what we have seen, the binary rule of binary addition has been applied. Now, binary multiplication. Now, binary multiplication is the same to our decimal multiplication. Again only the multiplication rule is different. That means, here again there are only 2 digit numbers 0 and 1. So, what we can say, that what are the basic rules? See, for binary multiplication, again this can be 0 into 0, it is defined as 0. Then again 0 into 1, then again it is 0, then 1 into 0, obviously that will be 0, and then this is 1 into 1, again this is a 1. So, this only this multiplication is different and addition will be just now the binary addition we have defined, that we have to do. Now, if I apply, say I have two such operands, okay. Say I have these two operands I want to multiply, 1 0 1 1 1 and 1 0 1 1. So, the 0 multiplied by anything, already we have seen that will be 0. Then again I am giving the cross, this will be multiplied by 1. So, 1 multiplied by 1 into 1 1 and 1 into 0 0. So, the same thing again, that it will be multiplied by 0, then it will be multiplied by 1. Now, only binary addition I have to apply. So, this is 0. Now, 0 plus 1, already we have seen 0 plus 1 is 1, 0 plus 1 1 and 1 plus 0. So, this is 1. Now, 0 plus 1 1 plus 0 1, 1 plus 1 sum 0, because we know 1 plus 1 is sum 0, but carry 1. So, this becomes now sum 0 carry 1 carry 1. So, I am giving 1 carry 1, okay, carry 1. Now, if I add again 3 0 means 0 and 1 plus 1 0 carry 1. Now, again 1 plus 1 0, 0 plus 1 1, but carry 1, again 0 plus 0 plus 1 1 and this one 1. So, this is my result. So, the similar, the addition rule, binary addition rule is applied, and only the multiplication is slightly different, otherwise the total multiplication rule is same as that of our decimal notation. Now, we see that our today's quiz question, that lecture 4 quiz. The first thing is the convert the decimal number 0.252 in decimal base to binary with an error less than 1%. Second is convert the following decimal numbers to hex and binary coded hex. So, that this is the two decimal numbers are given, one is pure integer, one has the integer as well as non-integer portion, and we have to convert that thing to hexadecimal numbers as well as BCH, the binary coded hexadecimal. Now, convert the following binary numbers to octal and binary coded octal, and this is very similar to the question number 2, but only the binary is itself given. And write the ASCII code for the message. The email is digital@iit.ac.in. So, that means I want that this, what will be the ASCII code of this message if when I type this, message that the email is digital@iit.ac.in, then how it is converted to that ASCII. So, to do that thing. So, these are the 4 questions for lecture 4 quiz. So, today we end at this point. will continue the digital logic lecture 3, but before that we quickly go through the answers of the last day's lecture quiz. So, the last day's quiz, there are 4 questions given and we see the answers. The first question was the convert the decimal number 0.252 decimal to binary with an error less than 1%. Now, as the error is 1%, so the what will be the error on 0.252? So, we will be multiplying this thing by 0.01 into the number 0.252. So, this is equal to 0.00252. Now, the truncation error, that means when we convert the decimal number to the binary, up to what digit we will convert it. So, if it is up to n bits, that means after decimal point if we take the value up to n bits, then we know the error is 2 to the power minus n. Last lecture we discussed that thing. So, this error should be less than this 1% error, means 0.00252. So, 2 to the power minus n is less than 0.00252, that can be written as 2 to the power n greater than 397. So, from this expression we can get the n if I take the log on both sides, then it will be log of 397 divided by log 2, and this is value equal to 8.63. Now, as n is the number of bits, so this should be some integer value, and that is why we are taking the nearest integer is 9, that is my nearest integer. So, when we convert 252 as binary, then we have to, if we take the number of bits after decimal point is not n, means n equal to 9, that means if you take 9 bits, then it will be, the error will be less than 1%. So, that means 0.252 in decimal is equal to 0.010000001 in binary, that means 9 bits after this decimal point. Now, we see the next question. Next one is the convert the following decimal numbers to hex and binary coded hex. The first one we see that 584 is the number. Now, 584, if I